Good morning and welcome to the demonstration of Photoview Plus, the Lista 4D module for advanced photometric and spectra data management. Let's start taking a photometry coming from a gonio photometry at our gonio photometer, and we drag and drop it into Photoview. It's clear that whenever you get a file from a gonio photometer, you have to fix the metrics because, for example, the values you have over here, just a second, I fix 2 decimal points. It's clear that the values at gamma 0, even though you fix perfectly the luminary at the gonio photometer, it is not coming exactly like the theory, so exactly with the same value. So the first thing you have to do is to, in a way, manipulate the matrix and normalize it in order to have the values at gamma 0 and at gamma 180 in case. This is not the case because the photometry is only downward. So we normalize the photometry. And so, as you can see, all the values now are perfectly the same. So this is usually the first step. Then the second step is, in case, check the efficiency, because this photometry was taken in the absolute way. So the efficiency is 100%. Sometimes, if you apply some of the available features over here, it is necessary then to apply 100. It means to bring back the efficiency to 100%. So whenever, for example, you turn the matrix, the interpolations are giving you, let's say, little errors. And so you can fix them using 100%. Other available features are the constant one. So over here you can equalize constant, you can add a constant, you can multiply by a constant, or you can divide by a constant. This is the case, for example, whenever you have a photometry that is going upward and the stray light arising from the lab is giving you some information that it is not expected. So you want to remove it. So for example, for a luminary, for road lighting, it is usually a luminary. Most of the luminaries now available in the market, they have a flat glass. And so it is clear that there is no light going upward. But whenever you finish your photometry, you will find that something is still available at the upper part of the photometry. So using multiply by constant or equalize by constant, you can select a part of the matrix. You can multiply or equalize by constant. If you place 0, then your photometry, the selected planes and selected angles, in this case, will be put to 0. And so you can erase, you can remove the stray light. It's clear that the stray light is affecting the whole photometry, but it's very difficult to manage in this way the downward part of the photometry. It should be done a different measurement. So for example, you take the complete measurement and then you had a circle and run a circle exactly in front of the luminary, and you run the photometry again, and then you subtract the main photometry with the stray light photometry. So the photometry arising from just measuring the stray light. In this case, we can come to a very little value, but usually, for example, the experience at our lab says that usually we have a stray light not higher than 0.5, 0.6%. So it is quite a little value. Then we have other features over here, like the average. We can select two planes and average them. Then interpolate, we can select a plane. So for example, let's say that for any reason you have a peak in one of the values. Using interpolate, this peak will be interpolated and so removed. Then we have right equal to left, left equal to right, whenever you want to make equal the same one part of the photometry to the other. Then flip on axis. This is quite an interesting feature. So for example, whenever you have a special photometry and you want to turn it, you select one plane and all the photometry will be tilted in function of the selected plane. Adjust, it is a feature adjusting the metrics. Copy and paste means that you can copy a section of the photometry, just selecting the planes, and then you paste at a different location. Then Z rotation, it means that whenever you have a matrix and, for example, you didn't place the luminaire at the proper way at the goniophotometer, so with the proper orientation of the different planes in function of the luminaire, it is in any case at this stage possible to rotate the luminaire. So for example, let's say that this is, as you can see, a complete rotosymmetrical photometry, but in this case it is possible to change and to rotate about the z-axis 90 degrees, but you can fix any value you want. Then tilt angle. This is another interesting feature. So for example, whenever you measure a luminaire that, for example, a wall luminaire that it has a tilting angle of 45 degrees, usually the commercial people, they would like to have exactly the photometry in function of the installation of the luminaire. So the photometry should be tilted 45 degrees, for example. So in this case, we'll tilt along the C0, C180 axis, or we can select also the other. And once we execute, you will find that the photometry will be tilted 45 degrees. Whenever you confirm, then the photometry will be brought to this new tilting angle. Symmetrize, it is another interesting feature. So for example, in this case, if we don't want to have the complete matrix, as we could see, this is a rotosymmetrical luminaire, then we select rotosymmetric, and then all the values will be brought to a single plane, which corresponds to all the others. But as you can see, it is also possible to have different features. So starting from the asymmetric photometry, which is this one, from the point of view of our way we measure, asymmetric means that we consider all the photometry, so starting from 0 going up to 355 in case we have a step of 5 degrees on C. Over here, you can also switch from one step. So for example, in this case, you can see that the step in between two planes, two half planes, it is 10 degrees, but it is possible from 10 degrees to move down to 1 degree. So for example, this is what we do whenever we approach a calculation, we approach a line calculation, or whenever we approach a diagram like the polar diagram, like the isolux curves, etc. We always expand the matrix to 1 degree on G, on gamma, and 1 degree on C. It's clear that in this case it is also possible to select the maximum gamma angle. So you can expand from 90 degrees, which is the maximum value now available, to 180. Convert, it is a feature that was very useful in the past whenever we had to convert from one measuring system to the other. So for example, as you can see here, we have CG. Usually with CG, we mean a generic photometry in C gamma. Then we have C gamma for road lighting. So the first plane over here, in place of being 0, it will be 270. And so we have C gamma roads following CIE 34, which is the first recommendation introduced many, many years ago about road luminaires. And then we have C gamma rotated. It means that it is possible to rotate the luminary 90 degrees. So for example, in order to consider the American approach. Down here we have VH. It is the old measuring system available for floodlights. So it is also possible to switch from one, for example, in this case, we have a C gamma because we start at 0, C gamma matrix. We can switch it to C gamma for roads, but we can also switch to VH. It's clear that doing that, not having the different points at the matrix, the perfect correspondence in between one to the other, then we have to apply some interpolations, and the interpolation is bringing a little error. Then you can correct with 100%. The difference you find here once you've finished the conversion, it is the error that you bring with such an operation. It's clear that whenever you have a very dense, very high with a matrix with a high resolution, it is possible that it is quite mathematical that the error will be lower and lower. Then over here, we can also copy. We can copy in the asymmetric way and inverted copy the matrix. So in this case, we create a second matrix of the first available one. And then convert the spectra into intensities. So we come back to this point later on when we introduce the spectra management, because the program Photoview Plus is capable to manage goniospectrometry, and it's clear that whenever you have a goniospectrometry, so you measure the spectrum at any position of the matrix, then it is possible from the spectrum to convert it into illuminance, and then from illuminance into intensities. So it means that in place of running a goniophotometry with a lux meter, you can run your goniospectrometry with a spectroradiometer and then convert the information arising from the spectra to intensities. But we can back to this point later on. So now we have fixed, let's say that we finished to fix the matrix. We come to this section in order to define the information related to the measurement and related to the luminary. So at this section, you need to input the information about the code, the name. The line means, for example, type A. It is the family name. Over here, you can input the you can input the company name. This is the name that will then appear, for example, at the top of the LDT file. Then, as you can see here, there are no dimensions. You have to define the dimension of your luminaire. So you have to select the shape, circular, rectangular, the length in millimeters. So let's say 550, the width 250, the height. If we select circular, then we just define the diameter, and then in place of the width and the length, and the height of the luminaire, let's say, is 150. Then you can select over here if it is mounted to the ceiling or not. Then you confirm. Next step is the definition of the luminous area. Over here, again, you select in between circular and rectangular. You define the length, so let's say 140, and the width is 100, and let's say that we have no side emission of the luminaire, so we leave the height at 0. The luminous area, the luminous volume is not available. There is only a luminous area. Okay, so at this stage, the program has to recalculate these parameters about the upper horizontal luminous area, lower horizontal luminous area. In this case, there is no horizontal luminous area. It is the lower horizontal luminous area that was calculated. It is also possible in case the height is not equal to 0 to input over here the related values. Why? Because sometimes there are it's very rare, but sometimes there could be some luminaires emitting on one face and not on the other. I repeat, very rarely. On the right, we come to the measurement data. So the code, the measurement name. So more than a measurement name, this is a measurement description. So for example, you can input over here that the measurement was done on this luminaire LED high bay light, but with louver. I don't know. This is a sort of descriptions, or most of the times, so for example, over here in our lab, we also input a description about, for example, the lenses, the driver, and so on. And if the space, the length of the available characters, the total number of the available characters are not enough, we can then use the notes over here, the remarks, that will be saved then to the final file. We come in short time to show you that it is possible to save all these information into the Excel file. So the date, the laboratory is Oxitec, and the operator. And the temperature, this is taken automatically from the file, and humidity either. And the airspeed, 0, 1. At this stage, it is possible to input the instrument list. So, for example, we made this consideration that it is necessary to link exactly which were the instruments used for the measurements. So usually we select this one. We can input over here a very short description of the available luminaires, but if you want, it is also possible to select the instrument list, and from here load for example, the table. We come to the desktop, program-based data. Okay, so for example, we prepared a list of tables, and so no chance. Okay. But it is also possible to input over here all the other instruments. It is simply done in this way, head tool, and from here you input all the instruments, and then you can save your table. So it means that whenever you save at the end your information, you're going to have not a single file for the photometry, and all the other information are spread over into different spreadsheets or into different text files, etc., or into different lists. It is all packed at the same location at the Excel file. Okay. Other information, important information, which cannot be managed, for example, through the LDT file or through the IS file, are the electrical parameters. So we have the option to manage two different set of parameters, electrical parameters. For channel 1, usually it is at the luminary source point. And then this one is after, for example, the driver. If you want to check what is, for example, the current on the LEDs, it is possible. If you have a multimeter with double channel, you can do that, and then all the parameters would be brought over here. It is then also possible, for example, to input the values at the end. You input the value and then you apply. The program is also carrying other features. So, for example, the flux and power in function of the current. Over here, it is possible to input all the values corresponding to the different configuration of your driver. And so you're going to have different values for flux of power in function of the current. So it means that in place of having many files describing the curves, so for example, many manufacturers, they are now producing many files, many LDT files in order to describe how the luminary is behaving. In this case, all the information are packed at the same location, and this is really a question of time saving, because whenever you want to check how the your luminary is behaving, then through here it is possible to define a certain current value, and then you can come to the flux and power, corresponding flux and power values. Standard table, again, over here, it is possible to upload a table, for example, over here, because you have to define, because our standard for photometric measurements of LEDs is saying that you have to perform the photometric and spectrometric measurement following certain parameters. And so it is essential that whenever you have a file, you declare which was the standard that you used for your measurement. And this feature is helping you, again, to keep all the information at the same location. And then there are uncertainties. All the most important standards for photometric measurements of LEDs, they are carrying out the concept of uncertainties. So you must give those information to your customer because this is part of the standard. So again, it is the case to present to your customer a PDF document where you put the uncertainties, or on the other hand, you can have all the information packed at a single file, again, the Excel file. So once you're here, another interesting feature of the program is the image manager. So up to now, we have been working with blind files. So the LDT file that was introduced on 1990, it is a file not carrying any image. So you just have to check, if you want to check the file and you want to see what the luminary is, you have to go somewhere else. In our case, it is very simple. So over here, we select the product images, and from here, we simply drag and drop from here into here. So we may have up to 4 images, and it is very interesting that because, for example, at the 4 images, we can also include, for example, an image about the driver, an image about the lenses. So whenever you want to check, you simply double click at the image, and the zoom will be applied, so you can analyze the driver. So again, all the information packed at the same point, at the same file. Again, for example, you may want to have an image about the references, how the luminaire was fixed at the goniophotometer, or you can also include the references. So, for example, how you associate the luminaire to the photometric measuring system. Tool, you may also add some images, and this is done, and at the end the images will be printed together with a list of instruments, because the program, whenever you have an OXL file, it is then possible to print a photometric and spectrometric report, including all the information related to the measurement and to the luminaire. And this is done in a very easy way. So, for example, we come now to set up custom print. We define that we want to have the report content. We want to have the report cover, simply doing the drag and drop in this way, instrument data, measurement data, report, test data. And then we start with the elaborations coming from Photoview Plus. And we confirm. And once we want to visualize the report, this is done straight away in this way. So this is the test report, including the context, instrument data, with, you can see here, the environment conditions and the electrical parameters. We have measurement data and the image of the luminaire. Again, the image of the luminaire. In this case, this page should have been placed at the beginning. And after that, we start with the performances of the luminaire under test. Okay. This is for data input. So in order to prepare our photometry to be used then and to be elaborated through the features included at the Photoview Plus. Which are these features? So let's say that our program can be downloaded from our website in the so-called open version. It is the freeware version, which is including this option, the polar diagram visualization, the Cartesian diagram, the UGR table, and the Solner diagram, and the energy efficiency assessment. On the other hand, from this icon onward, these features are included at Photoview Plus. So, for example, selecting this one, it is possible to visualize the photometry in 3D. And over here, you can have also the beam. You can see the beam over here in 3D. Over here, it is also possible to select and change a little bit the configuration of the visualization. So for example, if the solid color is not the proper one, you may switch to yellow to orange. So just clicking on here. You can also select the strength of your light focused on the photometry over here. You can from here rotate in the same way I showed you, because through the left bottom of your mouse you can rotate your photometry, and through the right bottom of your mouse you can move, you can pen, and through here you can rotate either Z rotation. It is done in this way. We can visualize the surface. We can visualize in only the surface or in the wireframe mode. It's up to you. Then over here we have the beam, and the beam can be visualized in a 3D way, or in a section along the C0, C180 plane, the red one, or 90, which is this one, CD. And over here, you had over here, you also have the height. So it means the distance from the luminaire. This is where we have the luminaire, and here we are at 1 meter from the luminaire, 2 meters, and up to 5 meters in this case. But let's say that this is good for a small spotlight. But in case of floodlights, very powerful floodlights, it is not the case to keep 5 degrees, but 5 meters. But you should place, for example, 50 meters. And so automatically the visualization will be scaled to 50 meters. Then the maximum percentage. It means that over here in Europe, we usually take 50%, but for example, in the States, NEMA says that you should consider up to 10%. What does it mean? It means that you take the value of your photometry at gamma 0, and you take the 10% value. So for example, you come here. So this is the value. It is 300 and let's say 50, more or less. We calculate the 10%, so it is 32. So you get the intersection over here, and from here to here, you draw a segment, and the opening of this segment will be the half beam of your luminaire in that plane. On the other hand, if you consider 50%, you just take the 50%, so it is something around here, and so the beam will be lower than the value before, and so it will, the program will automatically draw this one, giving you the angles. So in this case, we have an alpha value of 57 on here and 57 on here. So you have to sum to have the complete opening, the complete beam. Same if you come to the C90 beam. It is, as you can see, pretty the same value as before if we sum. And this is the visualization following NEMA. So the American standard, where over here you also have all the different values arising from the NEMA, and at the end also the beam class 7x7. Another feature is the zonal flux. The zonal flux gives you how the flux is distributed in function of the different angles starting from 0. So, for example, in this case, we consider 30 degrees opening. So it means that we have an opening more or less like this. And whenever we go up 60, 90, 120, 150, 180, we have that it is clear that whenever we have very close to 90 degrees, all the flux comes to 100%. And you can have the values over here and the total zonal flux split into different angles, as you can see here. Over here we have the values arising from CIE 52. It is the classification of again the classification of your photometry in function of the room index. So in function of the room index, you have these values and this classification of the photometry. It is a very, very old way of managing the photometry. Let's say that it is rarely used. Over here, we have, again, a summary of what you can find here. And on the right, we have the different classifications of the flux in function of the, for example, the CIE flux codes, the CIE photometry classification. This one is quite used still now, but this one is, I never had a chance to see once this classification used in the photometric papers. Then we have the DIN classification, the photometric classification, the French one, the UTE, the NBN, the BZ classification, typical of, again, a very old photometric classification from the British and from Belgium. Down here we have the LOR, ULOR, DLOR. So this is the total efficiency. This is the upward light output ratio. This is the downward output ratio, utilization factor. So other ways to consider how the flux is emitted in the space. At the end, this one is the RN. It is used usually for light pollution, sky light pollution. And this one is the ballast lumen factor, one rarely used. And this is the Italian classification of the luminaires for outdoor lighting, especially for public lighting. Let's now come to the CIE utilization factors. This is a table that was very used in the past. Let's say in the 80s, a little bit less in the 90s, and then it disappeared because more and more now we use lighting design tools. So we use the software to do what before was done manually. So the manufacturer supplied you this table, and from this table it was possible, given an average value of illuminance, to achieve for example, on the working plane of your room, then it was possible to define the total number of luminaires to install, which were then installed in a regular way. Now we are more flexible with the software, and so we do not use anymore this table. Down here, we have the calculation of, for example, the spacing criteria in function of the different planes, the main planes, so the C0, C180, and the C90, C270. And this is the sort of, not the spacing criterion, but the spacing to height ratio coming from TM05, so the British classification. Next, the isolux. It is possible to define a volume. It is to define a room, And over here you have the dimensions, and from here you may select absolute percentage per unit. So this is the way to visualize the values over here. You can modify the working plane. You can modify, for example, the values. So in case you do not want to visualize too many curves, you have the minimum at 150, the maximum at 700, and the delta, I want to have it at 100. So we reduce the total number of curves to be visualized. And over here, it is possible to define the different colors. So for example, if you do not want to have the white color as a background, you just click on the color, and from the the window over here, you can select which color you prefer. Isolux text color, same as Isolux or fixed through here. So you have many options to fix your visualization. Okay. It is also possible, so for example, to visualize the luminaire, but it is also possible to add a second luminaire in case you want to show your customers how in a very easy way, how your luminaire is behaving together with another of the same type. So change position, you can double click on here, or you can change position, selecting this option, show axis or not, show the text. So it means that in this case, we are visualizing exactly the calculation made by the program at any point of the grid you have over here. So we may have also the shading. It's clear that using the shading, which is based on shades of gray, it is the original color, the background color would be removed and replaced by the shades of gray. Then we can visualize the maximum value and again the luminaire. So next is the ISO candela diagram, and this is the diagram through which you can visualize how the flux is spread over, and in this case it is projected to a sphere, but we have different ways of visualizing. So this is again to a sphere in the orthographic way, in the equal area way, in the stereo way, sinusoidal projection, and the Cartesian projection. So from here, it is possible to turn the luminaire. Over here, we are giving a tilting angle, so you can see that the flux is directly in a different way. So let's say that we prefer to visualize in this way. So whenever you tilt the luminaire, you have the flux that is moving, and so it is changing the visualization of the isocandela diagram. So let's bring back to 0. And the rotation. So along the vertical axis, we can rotate the luminaire. In this case, it is quite the same. But if we consider, for example, road luminaires, you will see that it is clear whenever you turn it. So over here, we can visualize all the upper part and the lower part. So for example, in this case, being the photometry only downward, then you can have the flux only downward. And so it is not necessary to visualize also the upper part. But if you have a luminaire also emitting in the upper part, it will be interesting also to show that. So you can show over here the throw, down here, the value. You can show the maximum, and you can show line and numbers. The line numbers, the numbers over the lines. Then next, the luminance. The luminance is the luminance table, and the luminance diagram is something that may be very useful whenever you have to analyze your photometry from the point of view of the, for example, of the emission at certain angles, to define the total luminance along a defined gamma angle, like in this case. So, for example, some standards are saying that below a certain value or at a certain value, there shouldn't be more than 3,000 or 5,000, depending on the different standards. And this is helping you to visualize in a very quick and easy way how the luminary is behaving. So you define the line of reference, and if the line coming from this selection is inside the reference line, then it is good. Otherwise, if it is out, it is not good for the purpose, for the target. Then this is a diagram. Let's say it is the efficiency diagram for mostly for road luminaires. It means that you define the pavement and you define the road. And so, for example, in this case, you have you may define a tilting angle. So we are, as you can see here, we are spreading light into another direction. So more flux will be spread to the road, less flux to the pavement. And this is done over here. And then you may change into angles or distances, the values over here. You can improve and so move from one side to the other. And you see. And down here, we have the different flux classifications for road lighting and also for exterior lighting. So we have the spread, the throw and SLI from NEMA, the CIE cutoff classification with the definition of the maximum at C270 gamma 1. In this case, the ISNA cutoff, the DIN class. Again, over here, the DLOR, the downward light output ratio, the upward light output ratio, the efficiency, again, the light pollution, so the percentage of the flux going upward. And over here, we have the luminous intensity class of this luminary in function of the EN, the standard EN 13201. And again, through the same standard, the glare index for, this is usually for road lighting luminaires, and this is for environmental, for general purpose public lighting. This is the BUG. It is coming from the IS standard TM15. And it gives you the idea how the flux is split into different angles. This is a very useful way to analyze how the flux is spread, because it helps us to run different considerations whenever we have to run a lighting design project. So usually, for example, some of these parameters were used. For example, over here in Italy, it was used for the law on public lighting, so that you have to respect, you have to fulfill some requirements for the UL, UH, and for a few other parameters. This system is also bringing to something very useful from the point of view of the photometric analysis. So the so-called BUG. The BUG is a system where you classify the photometry simply considering the backlight, the upward light, and the glare. Through these values, a designer using a software with the capability of including also the BUG values, he can come straight away to the luminaire he is looking for. So, for example, if he is running the lighting of a certain area, he already knows which is the effect he has to achieve, and so it is then necessary to achieve a certain BUG. So he knows the BUG, he goes to the search engine and he finds straight away the luminaire. So he can analyze the luminaire not from the body point of view, how nice is the luminaire, but from the real performance of the luminaire. So it is really doing the lighting design work. And in this case, we also have how we classify the beam, type 1, type 2, type 3, type 4, etc., which is also summarized over here. And this is coming from NEMA. Next, the analysis of the usually this diagram, this table is used for emergency lighting, and in function of the different configurations of the luminaires we have here, we can come through this table to analyze whether, for example, the minimum lux it is achieved using this luminaire, the uniformity is achieved or not. So whenever it is achieved, it is in white. Whenever it is not achieved, so for example, it is not achieved in this case, the uniformity, then it is visualized in red. If it is achieved, it is in green. Next, latest two options. This is for the custom diagrams and tables. So, for example, all these features can be customized. So, for example, if you have a template, if you have a character, if you have a color of your own, we can customize the diagrams and tables in function of your needs. So, for example, we developed and implemented many customizations for our customers. Most of them related to the beam visualization and to the visualization of the diagrams. But we can customize anything you have here into your own. This one is the datasheet. This is possible to have. It is possible to have the datasheet whenever you input also the other parameters. Let's say the catalog and commercial data parameters, which are a part of the performances of the luminaire. So this information should be managed through our ListWin module. So let's say it works in this way. You prepare the photometry, then you import the photometry into the database, and through the database you have the option to add another set of roughly 90 different parameters in order to characterize your luminaires. So, for example, you can define the IP, you can define the IK, etc. You can define the product type, the environment, you can define the mounting. So there are really a great deal of parameters you can consider. Let's come now to the latest feature of Photoview Plus, which is the management of the spectra, or the spectrum of the spectra. Why? Because it is possible to manage a single spectrum. So, for example, whenever we have a luminary and we put the spectral radiometer on the luminous axis and we take the measurement, we get the measurement, then we have a single spectrum we can import, but it is clear that this spectrum is related not to the whole luminary, but to a single point. So simply drag and drop. The program will ask you to define the unit, irradiance, for example. We don't want to apply any spectra correction because, for example, if we measured using a spectral radiometer, then included at the list of available instruments, then automatically, whenever you import spectra, it will be corrected in function of the correction factor or the correction curve of your spectroradiometer. Over here, you define which is the standard you want to apply for the raw import, which is the data file I'm going to introduce shortly. And then we confirm. Sorry, I made a mistake because I didn't use the proper file. This is the file that it is automatically produced by our goniophotometer during the measurement, and it is the file including all the electrical parameters, the position, the voltage, the power, the frequency, and the temperature measurement, etc. So it is not a file that could be imported over here. We have to go to single spectrum, and we can import these file formats. So for example, a spectrum in CSV, a text file, an Excel file. So for example, if we have this one, we simply drag and drop. Again, we define, and that's it. So right now we have photometry and we have spectrometry all together, but again, simply considering a single spectrum. And this is the radiance measured, for example, at gamma 0. It is not an integrated spectrum. If you want to have an integrated spectrum, then you have to run a goniospectrometry at your laboratory. And let's import a goniospectrometry. So we go back and we select the raw file. The raw file is the file produced by our goniophotometers, and you simply drag and drop. Again, the program is asking which is the standard that we want to apply. In this case, it is for the calculation of the average spectrum. Over here, we have all the available spectra, and it is very useful because through this analysis, you can see if there is a color shift in between, for example, 0 degrees, gamma 0 degrees, up to 90 degrees. You know, sometimes the lenses, sometimes the glass, sometimes the same luminary, it is affecting the light emission. So it is switching from one color, for example, the color you may have at gamma 0 to gamma 75, gamma 80, it may shift to yellow. So at the center is white, and going to up to 90 degrees, it becomes yellow. And this is coming straight away through here because over here you have the analysis of any spectra, and you can define any color shift. Once you have finished, you confirm. And through here, you may find over here the integrated spectrum, the average spectrum, and any single spectrum coming from the Gonio spectrometry. The integrated spectrum is different from the average spectrum because the integrated spectrum is taking into consideration the weight of any area of your world, including meridians and parallels, you know, and the areas are different at the South Pole and at the North Pole compared to the areas at the equator. So the integrated spectrum is weighted in function of the different areas. Over here you have the color coordinates into 3 different systems: the X and Y, the U and V, the U first, V first. Then over here the program is also calculating the integrated flux. As you can see, this flux is different from this flux, because the luminary flux is the flux arising from the integration of the matrix. And as you can see, they do not carry the same value. It's clear because we are not using the same instrument. In one case, we use the lux meter. In the other case, we use the spectroradiometer. And so it is clear that the values are different. But this value is coming from the integrated spectrum. So if we go now back to this feature we had a chance to see at the beginning of this demonstration, we may convert this matrix into the matrix arising coming from the Gonio spectrometry. And at the end, we bring to this value. Then over here we have the CCT value coming from the integrated spectrum. But as you can see, in function of the different selection, you may have different values over here. So then we have the standard we applied for whenever we did the import. Then the measurement distance, the calculation of the DUV, the delta U first, V first, and then the CRI calculation over here with the CRI related to 8 samples and the CRI related to 15 samples. You know that at a certain point the 8 colors were not considered enough to give the proper value of the CRI, so they were extended to 15 samples. Over here we have the scotopic over photopic ratio. If you want to run a calculation, let's say for example, for road lighting, considering that we are during the night and the vision is different, from photopic we go to scotopic, and this is the parameter, this is the value 162 that you should apply in order to switch from photopic to scotopic. Again, melanopic ratio over here in function of the standard you can select over here. At this section we have the spectrum selection. In case you want to not to use the drag and drop we used so far, you can select from a window, pass the spectrum from the clipboard. So for example, if you have a spectrum, a single spectra, you open it, you select, and then you copy and paste. Control C, and through here you passed from clipboard. Again, it is asking the unit. You may also say that we have total radiant spectral power. So this spectrum, in place of being considered as a single spectrum, it is an integrated spectrum. It is not usually correct. Maybe sometimes you have a single spectrum coming from the sphere. And so in this case, you have an integrated spectrum, and in place of considering 1 unit of radiance or irradiance for a single point measurement, you consider the integrated value. So let's go back, and that's it again, the same value. Over here, export, if you want, you can select one or more, you can select, in case you have a Gaussian spectrometry over here, you can select a single spectrum, and then you can export spectra, or you can export the complete spectrum list. You can export the average spectrum or the integrated spectrum. Then over here, we have extra data that you may input in case you want to save the information related to the ISTM 2714, which is the first standard that was introduced many years ago, let's say 10 years ago. This is a work done by Jan Estan and the committee from the IS in order to manage a file for spectrum, for the spectrum. So over here, you have the option to introduce the different parameters in order to characterize your spectrometry. And in this case, if you have an irradiance value, you can switch from normalized to unnormalized. Okay. Field, light, yes, because Photoview Plus can manage the spectra in the visible field. But Photoview, in general, it is capable of managing also horticultural data, UV data, and radiometric data. Let's stay with the visual. And from here, we can switch to the right part of the monitor and visualize the different color spaces in function of the different standards. Over here, you can select what you want to print. So for example, if you want to print the ratios, you select the ratios. If you do not want to print the IS TM30, we come straight away to see what it is, or McAdams section, the CRI section, etc. You unselect them. Let's print together. So this is the visualization of the CRI in form of chart and in form of pie cake. Then we have the McAdams ellipses. So in this case, you have the single point. Okay, it is this black point. But let's say that we have a Gaussian spectrometry. Let's go back to the Gaussian spectrometry. We confirm. And then, as you can see, it is no more a single point, but the integrated spectrum is the black one, and all the other points corresponding to the different spectra, they are visualized in this way. So this is a very simple way to analyze if your photometry is a constant from the point of view of color in function of the different angles. And over here, it is giving you the classification coming from the ANSI C78376. Then over here, we can visualize all the diagrams arising from the TM30 analysis, the complete set. And last but not least, the spectrum analysis. Over here, you can analyze the spectrum from the different bandwidth. So the visible, and then split into blue, green, yellow, orange, and red. And over here you can select, for example, if you want to visualize only one part, it is then possible to select one, and the program over here will show you exactly that part of the spectrum. But let's say that now we have prepared all the information, and where do we save all the complete set of information we included at this photometry and goniospectrometry? We have different options. So whenever you select File, Save, it is possible to have all these options. So for example, you can select into an LTT file. It is clear that in this case, we only save the photometry, and all the other information will be missed if we close the program. Then IS, LM63, again, only photometry. CIPSI, the old TML format from the British, again, only photometry. We come back, Gonio is our format. The LTL, again, from the Nordic European countries, Denmark, Sweden, they introduced this format, which is like the British one. It is no more used. The CEN, the 10 format, the CIA format, pretty closed, almost never used, apart from the CIE, SASTAN from the Australians, and they still use this format. And then we have these two formats, file formats, the UNI 11733 and the TM33 from the IS. These files are pretty the same. They have the same file format, especially for the first 5 parts of the file. Because they came from a cooperation in between UNI, which is the standardization body of Italy, and the IS. So with these file formats, it is possible to save photometry and spectrometry altogether, and some of the parameters we included. But for example, all the information about the instruments, the uncertainties, the standards, the flux and powering function of the current curves, the images cannot be saved. The only way to save them is through the OXL file format, which is carrying all the information. So let's say that the OXL, from our point of view, it is a file that was specifically thought at the beginning for our lab. It gave us great improvement to our work step by step, and it is a file from which we can convert to all the other file formats. So coming from the experience at our lab, we suggest to use our OXL because the photometries would be much easier. Also in function of whenever you want to use this file format for other applications, for example, for web applications, we have some web applications where we can convert all the photometries, diagrams, spectra, etc., into visualization directly available through the web. So it is quite a powerful tool for the management, for handling your photometries. Okay, that's it. Thank you very much. So have a nice day. Bye-bye.